Hello, beautiful humans. Trying something new. Bear with me while I figure this out. Okay, let's see here. Okay, all right. So what we're going to do today is talk all about polynomials. It's going to be quite a lot of information, so make sure you are ready for some new vocabulary, some important concepts, and really get your thinking caps on. We're going through a lot right now. Okay, so what is a polynomial? A polynomial is a multi-term expression, right? So we have a quadratic is a multi-term expression, typically with 3 terms, right? We have our squared term, our linear term, and then our constant. An equation of a line is also a polynomial, so we have some examples there. A couple things it cannot include. You are not allowed to divide by a variable, which means you cannot have a negative exponent on a variable because that means that that variable is in the denominator, right? So that's not allowed. You cannot have a radical or a fractional exponent. So you can't have a radical within a variable inside or a fractional exponent. Those things are not allowed. So a couple of things that cannot exist for these to be polynomials. A couple non-examples there for you. So a rational function is not a polynomial. All right, the degree of a polynomial is going to be the highest exponent value of the variable. If there are multiple terms together, like y cubed being multiplied by y, or x cubed being multiplied by y to the 4th, you're going to actually add those exponents together to determine the degree of that term. The degree of the entire polynomial will be the highest exponent value, the highest degree of each of the individual terms. So if we look at this example over here, the first example, I noticed the largest exponent value there is a 5. So this is a degree 5 polynomial. This is not written in standard form. Typically, if it's written in standard form, we go in what we call descending order, the greatest exponent value all the way down to the least exponent value. So in this case, this is not written in standard form, so be careful of that. You're looking for the highest exponent value. Now, this next one is in descending order, and the highest exponent value is 8. So that's a degree 8 polynomial. This thing is not a polynomial, this third example, because of this negative exponent here. This actually means 1 over x to the 3rd, right? And we are not allowed to divide by variables in polynomials, so not a polynomial. All right, what about this one? Well, this is in factored form. We have our factors listed out here. If we wanted to put this in standard form, we'd have to do area models, multiply it all out, multiply. But really what we're going to end up, the degree will be how many total x's do you have? So I have 2 x's here times another x, that would be x to the 3rd, times another x, that'd be x to the 4th. So this is going to be a degree 4 polynomial. Okay. In this one, right here, we have 2 variables coming together. This is y to the power of 1. To determine the degree of this term, we're going to add those 2 together, and we're going to say this is a degree 3 right here. So that's a degree 3 term. This is a 2, this is a 1. That's a constant, no degree there. That's a 0, right? And so this is going to be a degree 3 polynomial because the highest exponent value there is 3 when we add those 2 together. All right. What is the leading coefficient? The leading coefficient is the number, the constant, in front of whichever term has the degree. So if we looked up at this first example here, the leading coefficient would have been -3 because that x to the 5th is determining our degree. The leading coefficient goes in front of whatever variable determines our degree. So it would be 9 in this example. It would not exist in the third example because this is not a polynomial. When we multiply this whole thing out, there's a 1 in front of here, a 1 in front of here, a 1 in front of here. So the leading coefficient of that example would just be 1 because when we multiply, nothing's going to change in front of my x value there. So that would be a leading coefficient of 1. And then in this last example, it would be 2 because that is our degree term there. Okay, so in these examples here, the leading coefficient is -3, again, because this is not in descending order, so we have to look for that leading coefficient. And again, this one would be 9. Okay, what does it tell us? Well, the leading coefficient indicates what the end behavior is going to do. If you think about our quadratic, your leading coefficient is your a value, right? So we have positive a value, we had arms up on our quadratic, right? Arms up. When we had a negative a value or negative leading coefficient, we had arms down. So this leading coefficient indicates the right arm only. Now, when we have an even degree like quadratic, it determines both arms. But if we are talking about odd degree polynomials, we're really focused on the right arm here. So if you have a positive leading coefficient, if you have a positive leading coefficient, then your right arm's going to end up just like in our quadratic, right? Right arm up if it's a positive leading coefficient, just like a positive a value. If you have a negative leading coefficient, the right arm is going to face down, right arm down. So as x goes to infinity, y or f of x is going to go to negative infinity. Super important. So this leading coefficient indicates the end behavior of our function. So very important to know. Okay, multiplicity indicates how many times a factor occurs in a polynomial. So we break polynomials down into factored form, which they're not all going to be, but if we break them down into factored form, we can say there's multiplicity anytime a factor repeats. So if you had a square term, right? So if we had a quadratic, this quadratic right here, x minus 3 squared, this would be a vertex at x equals 3, right? In fact, the vertex would be 3, 0, because this vertex is on the x-axis. We also kind of call this a bounce point because it hits the x-axis and then it bounces right back up. So what was decreasing, right? So as we read this left to right, this is decreasing. It hits the x-axis and then it's going to be increasing. So we call that a bounce point. So when you have a double root like that, or an even root, in fact, or an even multiplicity, it's going to bounce. It's going to hit that x-axis and go right back off. So something to look for as we go through. So in this case, this term is going to have a multiplicity of 3. This factor occurs 3 times, so it's special. Also, this is a degree 5 polynomial because I have 1, 2, 3, 4, 5 x's, so 3 x's from that cubed factor, and then 2 more for my other 2 factors. Here I have 2 x's, and then 3 more, that's 5, 6, 7. This is a degree 7 polynomial, and we have a multiplicity of 2 on x equals 0, that's a double, and then we have a multiplicity of 3 on the factor x minus 1. Okay, we'll get more into that later. We're going to get into all of this in much more detail going forward, but this is a preview of many things involving polynomials. Okay, standard form we said is going to be written in descending order, meaning the highest exponent value first. So currently this is not in descending order. I know this term should come first because it has the highest exponent value. So this would be x to the power of 7. My next highest value is 4, or 5 minus x, 4x to the power of 5. And then we have a x to the 4th minus 3x cubed plus x minus 18. Again, every exponent should be smaller than the previous one if we write this in descending order. Okay, relative min and relative max refer to when you get polynomials like this, you're going to get lots of little what we call hills and valleys. So hills are going to be relative or absolute maximums, and valleys are going to be relative or absolute minimums. Not everything is going to have an absolute minimum. Not everything is going to have an absolute maximum, right? So in this example right here, there is no absolute minimum because this thing goes forever and ever to negative infinity. However, it does have an absolute max because there is no point on this function where it has a higher value or higher y value, right, than this blue point right here. This point, this pink point, is a relative maximum. It's not the absolute maximum, but it's a hill, right? So it's a high point on our function. So we call it a relative maximum. And then again, this is a relative minimum because it's a valley on our function. So we point those out. Again, not everything will have absolute. Most of them will have relative max and min as we go through. In fact, well, yeah. Okay. All right, leading coefficient test. So again, it tells us what the right arm does. So if the leading coefficient is negative, as it is here, right? So this is negative. Then the right arm of the polynomial will face down. In other words, as x goes to positive infinity, right? We're talking about end behavior here. F of x, my y values, are going to go to negative infinity. That will dictate the end behavior. All I need to know is this, and I already have a general idea of what the shape of this thing will look like. Okay, and then if the leading coefficient is positive, as it is here, then the right arm of the polynomial will face up. In other words, as x goes to positive infinity, f of x or y is going to positive infinity as well. So that is how, that's what the leading coefficient is going to tell us. It's all about what is that right arm doing? And again, it's the right arm only because in odd degrees, we have arms facing opposite directions, right? Okay. Highest degree test. So what does the highest degree tell you about the polynomial? It tells us lots of stuff. It's great. Okay, so the degree is, well, this highest exponent value here is 6. Then the end behavior of the polynomial will, okay, if we have an even degree, arms are together. So think about your quadratic. That's the most common example we've used with an even degree, right? Degree 2. Arms are together. They're either up or they're down. They don't go both ways, right? So arms together, up or down. So if you have an even, not 6. This should be even because this applies to all even degree polynomials. If you have an even degree, then the end behavior of the polynomial will be the same. As x goes to infinity, y is going to go to infinity or negative infinity, but it's going to do the same thing on the left and the right. So on the left or on the right, it'll do the same thing as it does on the left, those y values. So in this case, it would be f of x on both of these is going to positive infinity because we have a positive leading coefficient. So positive leading coefficient tells me the right arm is up. The fact that it's an even degree tells me both arms are together. They do the same thing. So both arms are going to face up. All right. If the degree is odd, as it is in this case, this is the degree 3 polynomial, then the end behaviors will be different. You're going to have opposite end behaviors, right? So as x goes to infinity, again, this has a positive leading coefficient. F of x is also going to go to infinity. That's what we learned on that leading coefficient. However, as x goes to negative infinity, f of x is also going to go to negative infinity. Notice different end behaviors. So what we have here is on the right, we're going to positive infinity. On the left, we're going to negative infinity. Different or opposite end behaviors, right? Arms facing different directions. That's what odd degree polynomials give us. Okay. Leading coefficient and degree, let's put it all together. What does it tell us about this and what does it tell us about the general shape? Okay, the other thing we need to come back to, what else does the degree tell us? Well, we didn't really spend detailed time talking about it, but it tells us, if you look up here on the definition, the degree tells us the maximum number of times the function can cross the x-axis. So if you think about a quadratic, right? If we draw our typical quadratic, it has 2 x-intercepts. That's the maximum number. But we also know we could have 1 x-intercept, right? That's still quadratic. We could also have 0 x-intercepts. So it doesn't tell us how many intercepts it has. It tells us the maximum number of intercepts it possibly could have. Okay, so that's what the degree is going to tell us. So if we have a degree of 5, so this is a degree 5 because that's my highest exponent value. And then my leading coefficient is going to be the number in front of that, which is -2. So my leading coefficient is negative, and I have an odd degree. Okay, well, negative means that the right arm is going to face down, right arm down. And then odd means they're going to face different directions, right? All right, if you think about a quadratic, boop, that is one valley, or if you faced it the other direction, it'd be one hill with a maximum of 2 intercepts. So we're always going to have 1 minus hills and valleys of our degree. So what I mean by that is, and sometimes these are a little awkward to draw, but let's see if we can do it here. So we're going to go up, down. That's 1 hill, 1 valley. 2 hills, 1 valley. Okay, so hill, hill, valley, valley, right? So we have 2 hills, 2 valleys for a total of 4, right? 4 changes of directions here. So always a degree 5 polynomial will have 4 possible changes of direction, because if we were to draw our random x-intercept, our x-axis there, right? How many times could this thing cross? 1, 2, 3, 4, 5. And that's what that tells us. So again, that degree tells us how many times it could possibly cross the x-axis. Of course, it could cross less than that. These hills and valleys could be shaped totally differently. This is just my rough sketch, given that this is a degree 5 with a negative leading coefficient. All right, so you try this one. This is a degree 8. We have a positive leading coefficient. So what do I know? I know my degree is 8, which is even, so both arms will face the same direction. I know that my leading coefficient is 1, which is positive, so both arms are going to face up. So I'm going to have an arrow up over here and an arrow up over here. 8 means I'm going to have 7 hills and valleys for a total of 8 possible crossings of my x-axis. 1 valley, 1 hill, 2 valleys, 2 hills, that's 4, 5, 6, and 7. Whee! To connect to my arrow that I put over here. Again, these could look really different, completely different than what I'm drawing. I'm just giving a rough estimate. This would have 1, 2, 3, 4, 5, 6, 7, 8 possible real roots, again, if that's where the x-axis were. Again, arms up because we have a positive leading coefficient, arms together because we have an even degree. All right, let's try this one. Negative leading coefficient, degree 4. So degree 4 means arms together. Leading coefficient is -5, meaning that the arms will be facing down. Okay, so then we have arms down, and we know we need 3 hills and valleys. 1, 2, and 3. That is an approximate of what this degree 4 polynomial might look like. Okay, ooh, this you tried. Pay attention, make sure it's in descending order. It is not. So this is a degree 5 polynomial. Its leading coefficient is then 5, which is positive. So I know the right arm is going to face up, which means the left arm is going to face down. And I need 4 hills and valleys. 1, 2, 3, 4. Like so, right arm up, positive leading coefficient, potential of 5 real roots on this guy, could look something like that. Okay, so let's talk about zeros. What else do we call zeros? We call them roots. We call them x-intercepts. We call them factors sometimes before we actually solve for them, right? Okay, so for a polynomial of degree n, it can have how many real zeros? Well, that's what we were talking about, right? How many times can it cross the x-axis at max? If it's degree 5, it can cross 5 times. If it's degree 4, it can cross 4 times. So if it's a degree n, it can cross n times. Okay, so what's the maximum number of zeros this polynomial could have? This is a degree 6. It could have a maximum of 6 real roots or 6 x-intercepts at max. Okay, this is a degree 3. It could have at maximum 3 zeros or 3 real roots, actual x-intercepts. All right, so how do we actually find these roots in factored form? Well, we're going to use zero product property, just like we always have. We're just going to have more factors this time. Property. You get the point. Okay, so how do we do this? We're just going to set all of these equal to 0 because remember, when we're looking for roots or x-intercepts, the y value is always 0. So we're just going to plug in 0 for f of x and solve for all of our possible factors. So when we plug in 0 here, now we have 2x plus 1 equals 0, right? That's one option. We could also have x plus 2 equals 0. That's another option. We could also have x minus 7 equals 0. And then we just need to zero product property each of these because if any of those terms equal 0, the entire thing will equal 0 because that's what happens when we multiply by 0, right? So when we subtract 1 and divide by 2, we get -1/2 as one of our roots. Over here, we're going to get -3 as one of our roots. And then we're going to have 7 as one of our roots. So these are the 3 roots. These are what this is what x equals, right? All of these are actually points, -1/2 comma 0, -3 comma 0, 7 comma 0, right? Actually where this function is crossing the x-axis. So if I wanted to sketch this one, I could be way more accurate than the last couple we did because I actually know where this thing crosses the x-axis. Cool. All right, so then let's look at this one. We have, this looks like a quadratic to me with an a value of -3 times that 5 value. So this is going to be a big negative a value. But again, doesn't matter. This is not going to change where I cross my roots, right? It just changes how tall or compressed or stretched this function is. So I just need to zero product property x minus 4 and 5x plus 1. We get x equals 4, and we get x equals -1/5. All right, So this one's going to give me x equals 3 from that first term. The next one will give me x minus 4. That guy has, x equals negative 4 rather. That's going to be a multiplicity of 2. That one counts twice. It's going to bounce. So when you go to graph that bounce point at negative 4, it's going to hit the axis and bounce right back up or down, depending on which direction it came from. So I notice we have a positive leading coefficient here. Positive leading coefficient. And this is a degree 1, 2, 3, 4, 5, degree 5. So the arms will face opposite directions. We're going to be up over here, which means we're going to come from down. Anyway, I'd have to figure out where all the other roots are. But at 4, we're going to get negative 4 over here. You're either going to get a bounce that looks like that or a bounce that looks like that. It's going to hit that axis and jump right back up or down, depending on where it came from. So when we have multiplicity, it affects the way the graph looks as well. So keep that in mind. Next term is going to give me x equals 2 over 5. Again, zero product property, all of that. And last but not least, x equals negative 1 over 7. Again, setting each of those terms equal to 0. All right, last but not least, this one would give me x equals 0 up front, x equals negative 1, x equals positive 1, x equals negative 3 has a multiplicity of 2. Again, that's a bounce point at negative 3. It's either going to come down, hit the axis, bounce right back up, or if it's coming up, it hits the axis and bounce right back down. Creates like a little quadratic, a mini quadratic on the x-axis. And then last but not least, this would be x equals 4 over 3. Okay, so we're going to use the x-intercepts or the roots to find the factors of polynomial so we can write the equation in factored form. Okay, so when you're looking at a graph, this is just like it's hard to write a quadratic in standard form from a graph, but it's a lot easier to write it in factored form. We're going to use that same exact concept for writing our polynomial equations. So I have a root at negative 6, a root at negative 4, and a root at positive 3. And I also have a given point here, which is going to matter when I'm solving for my a value. All right, so what are the roots? I have negative 6, 0, negative 4, 0, and positive 3, 0. Those are my roots. Convert to factored form. Well, that's like the inverse of zero product property. So it's going to be 6, or x plus 6 would be my first term. X plus 4 would be my second term. And x minus 3 would be my last one. So now I have factored form, but of course there's always an a value up here, or there could be, right? It could be 1, but it could be any other value. So we need to actually solve for it. Is it positive or negative? Well, this is an odd degree, right? This is a degree 3 polynomial. And on the right side, my arm is up, which means the a value is positive because the right arm is up, right? So it's going to be positive. The right arm is up. So how do I solve for a? Well, we're going to use this point 0, negative 0.72. We're going to go ahead and plug that in where we see x and y in our equation and solve for a. So what do we know right now? We know y equals some value a times x plus 6 times x plus 4 times x minus 3. We're going to plug in that value 0, negative 0.72 and go ahead and solve for our a value. So our y is negative 0.72 is going to equal a. I don't know what that is yet. That's what I'm solving for. 0 plus 6, 0 plus 4, 0 plus minus 3. Okay, and then we're just going to go ahead and multiply that out. So we get 6 times 4, 24 times 3, 72, and negative 3, negative 72. So now we have negative 0.72 equals a times negative 72. So we're going to divide by negative 72 on both sides. And we get, what is that, 0.001? A equals 0.01, just 1 0, right? Okay, so that is our a value. So if you go ahead and plug that into Desmos in front of your factored, you should end up with this graph we're given. So our actual polynomial equation is going to be f of x or y equals 0.01 times x plus 6 times x plus 4 times x minus 3 If you want to be really fancy and convert that into standard form, that would just be a lot of area models, right? Area model for your binomials, and then a bigger area model to multiply your trinomial by your binomial, and then of course multiply your a value in, and that would give you standard form. All right, oops, I already wrote that down here. Something happened with my formatting here. All right, you are going to try this one. Notice though, I'm going to give you a big hint. This thing, even though it's not exaggerated, this is a bounce point. So notice it hits right here, whoop, and then it's coming back up. It's not obvious, okay? But it does come back because then it's above here and then down again. So pay attention to that. Give that one a shot. Good luck to you. Okay, sorry, hold. Oh dear. Okay, here we go. Again, having some programming issues here. Okay, so on that problem, hopefully you identified that you had 3 real roots, -9, 0, -3, 0, and -2, 0. Now that -2, 0 is special. It's a bounce point. So this is going to be a double root or a multiplicity of 2, right? It counts twice, so it's going to be squared when we write our equation. Is the a value negative or positive? Well, my right arm is facing down, so it's a negative a value. So when you solve for a, double check, make sure you do in fact get a negative. All right, to plug this in, we know f of x is going to equal some value a times my first factor, x plus 9, times x plus 2, which is a double root. So we're going to square that term. Again, I can tell because it bounces right off. Notice how this one passes right through at that x. So we're still increasing. Okay, here we're decreasing, boop, we hit that point, and now we're increasing. Even though it's slight, it does actually go back up there, right there, okay? So it's a slight increase, so that is a double root. The other way you can think about this is if you notice you have 3 roots, but the arms are facing the same direction. So this must be an even degree polynomial. So that's going to indicate, hey, there must be some kind of multiplicity happening here. Let's look for that. Okay. So then we're going to plug in the point that we're given right here, which is -5, 1.92. So every time we see an x, we're going to plug in -5. Every time we see a y, we're going to plug in 1.92. We're going to go ahead and solve for a, and we get the a equals -0.03. Now this is good because we expected our a value to be negative, so that matches. Again, feel free to plug this whole equation over here into Desmos. It should match that graph above. Okay, last but not least, let's give this one a shot. This one is extra tricky because it has actually a multiplicity of 3. So right here, you'll notice there's kind of a cubic function. If we were to isolate this section right here and say, oh, let's just look at this little window right here. This looks like a little mini cubic function. So notice it's increasing, it kind of flattens out right there, and then it's increasing again. That's what our cubic functions have been known to do. So this is a multiplicity of 3. This is actually a cubed factor. Okay, so when we go over here, we have 1, 2, 3 intercepts, right? But and this is an odd degree. Okay, good. So we can have 3 intercepts, odd degree. That's looking good so far, except let's count our hills and valleys. We have 1 hill, 1 valley, a hill, and a valley. And I know, again, that hill and valley combo right there is very close together, but that's a 4 hills combination, 4 hills and valleys. This must be a degree 5 polynomial, so we're missing something, right? That's how we know that we have a multiplicity. And again, it's going to be 3 because it looks like a little cubic function, unlike our multiplicity of 2, which looks like a little mini quadratic, right? So it looks like a bounce point. Multiplicity 3 are going to look like little mini cubic functions. Okay, so right arm is facing up, so this must be a positive a value. So when I plug in my factored form, I know x plus 5 is going to occur once, x plus 1 is going to occur once, and x minus 4 counts 3 times, again, giving me my degree 5, and also accounting for that multiplicity over there. Okay, again, that's always when it happens on the x-axis. So either we hit the x-axis, bounce up or down, right? That's our quadratic, our double root. Or when we hit the x-axis right there, it's actually that kind of flat point of our cubic function. Okay, so then we're going to plug in our a, this point up here, which was 2,592. And we are going to solve for our a value. So when I plug that in, I get 2,592 equals A times 2,592, which means our A value is just 1. So I don't even need it there. You could put a 1 there if you really want to, but you don't have to. Hopefully this makes sense. Again, this is a lot, and this is just our first look at all of this. We're going to go into more detail and play with this a lot more going forward. Have a great week.